I think it's related to Professor Xiaoqin Wang's talk. Maybe it's actually related. Okay, let's welcome.
Thanks the organizer for inviting me. It's my honor to share my work on drawing causal inference from high-dimensional data. This talk is based on the joint work with Adam Liu, Chunhui Zhang, Jesse Saikang, Bin Yu, and Yuhan Yang. So somehow causal inference is related to AI, as cited by Judy Poole, who is a computer scientist and obtained the Turing Award. To build truly intelligent machines, teach them cause and effect. And also another machine learning researcher, Frank, wrote in his blog that causal inference is indeed something fundamental. This is not a question of whether you work on deep learning or causal inference, and in many cases you should do both. I think there are two frameworks for drawing causal inference. One is the potential outcome framework proposed by Lehman and then popularized by Rubin. And another one is the causal graphical model proposed by Judy Poole. I'm currently working on the potential outcomes framework. Under this framework, randomized experiments are golden standard for drawing causal inference. In traditional randomized experiments, the number of covariates is often very small. But in modern large-scale randomized experiments, we can observe many baseline covariates. So for example, so this is a figure from Wikipedia showing the use of a machine, PAC, the pulmonary artery catheter. The PAC is a monitoring device commonly inserted into critical ill patients. It provides several measurements of cardiac activities. However, the PAC is very expensive, and more importantly, inversion of the PAC is an invasive procedure to the body, so it carries some risk of complications, including death. Then the natural question is, should we use PAC? In particular, does PAC have effect on patient survival? Our original study found that PAC had an adverse effect on patient survival and led to increase the cost of care. This leads to some randomized experiments to verify whether this is a causality. So a randomized control trial called PAC-man was carried out in 65 UK intensive care units between 2001 and 2004. There were 1,013 patients in the experiment, and half of them are randomly selected who used the PAC, and the remaining half did not use the PAC. The outcome variable of interest is the quality adjusted life year, denoted by QLY. So a simple unbiased estimator for the effect of the PAC on QLY is the so-called difference in means estimator. However, in this experiment, we also observe many baseline covariates. For example, the age, the gender, and the estimated probability of death, and many health indicators. Some of the covariates are relevant to the outcomes. For example, the age and the estimated probability of death. And they show the imbalance between treatment and control group. In the sense that they have different means. The means of the age and the estimated probability of death is significantly different between treatment and control. And if we take their interactions into account, then the total number of covariates is more than 1,000, so it's very large. The question is, could we use the information in the covariate to help us to improve the estimation accuracy of the treatment effect? In general, there are a huge number of baseline covariates available in experiments. For example, in a clinical trial, the demographic and the genetic information may be recorded on each patient. And also in tech industry, where randomization is often called A/B testing, there's often a huge amount of behavior data collected on each user. However, in this big data setting, not all the covariates are relevant to the outcome of interest. So variable selection or some form of regularization is necessary to give efficient adjustment. Some variable selection methods, such as the AIC, BIC, lasso, and its variants, are of various options. In this work, we focus on study the asymptotic properties of the penalized regression-adjusted average treatment effect estimator. We also provide conservative variance estimator to help us construct confidence intervals. So the results of randomized experiments are often analyzed under the Neyman-Rubin potential outcomes model. In this model, suppose there are n experimental units which make up a finite population. For each unit I, there are two potential outcomes, y1 and y0, representing the unit receiving or not receiving the treatment. So the individual level treatment effect can be defined as the comparison of these two potential outcomes. For example, the y1 minus y0. However, in the experiment, since each unit is either in the treatment group or in the control group, but not both, so y1 and y0 cannot be observed simultaneously. Therefore, the individual level treatment effect is not identifiable without further model assumptions. However, their average over all the experimental units are estimatable. It is often called the average treatment effect, or ATE. So in this talk, I will use a ZI to denote the randomly assigned treatment status. For example, ZI equals 1 if the unit is assigned to treatment, and 0 if it is assigned to the control. And in the experiment, we also observe a p-dimensional baseline covariates. And for simplicity, we assume that the covariates are centered at mean 0. And the observed outcome denoted by y_OBS, which equals y1 if it is assigned to the treatment group, and equals y0 otherwise. So our goal is to draw causal conclusions from the observed data, xi, zi, and y_OBS. So under this, in the completely randomized experiments, both the xi, the potential outcomes y1 and y0 are fixed population quantities, and the randomness comes only from the treatment assignment, zi. So understanding the assignment mechanism is crucial for drawing causal inference in completely randomized experiments where the treatment group is sampled without replacement from the finite population. Then under the so-called stable unit treatment value assumption, the average treatment effect can be estimated without bias using the simple difference in means estimator. That is, the difference of means of outcome in the treatment group and in the control group. However, this estimator does not use any information in the covariates. So what if we have also observed many baseline covariates? For an illustration example, suppose here is the population we are interested in, and we want to study the effect of a new drug. Then we do a randomized experiment and randomly select half of them and give them the drug. If after randomization, we found that in the treatment group, there were more children. So the age in the treatment group and the control group are different. If we don't adjust for this imbalance in age, then the treatment effect cannot be estimated very accurately. So researchers often use regression adjustment to improve the estimation efficiency. A naive idea is to just regress the observed outcome on the treatment indicator and the covariates. However, it has been shown by Friedman that this method may hurt the precision. That means the asymptotic variance of the ATE estimator can be larger than the difference in means. The reason is roughly for this model, for this linear regression model, the y1 minus y0 equals tau for all I, which means the treatment effect is constant across all the experimental units. So if the treatment effect is heterogeneous, then this model is misspecified. So it cannot give a more accurate estimator. This problem can be solved by including the interactions between the treatment indicator and the covariate in the regression analysis. That is, we just adding the interaction term. Then we can show that the resulting treatment effect estimator is more efficient, at least not hurt the precision. This is equivalent to run two regressions. That is, regress the observed outcome on the covariates in the treatment group and in the control group. And in each group, we get a regression coefficient. And then we can estimate the ATE by the following equation. So this equation, you can see that these two terms is the difference in means. And for this term, so this is the mean of the covariates in the treatment group. And recording that the mean in the population is 0. So this term is adjusted for the difference of the mean in the treatment group and in the population. If the dimension of the covariates is small, then we can use ordinary least squares to get the adjusted vector. However, if the dimension of covariates is large, for example, is comparable to the sample size or larger than the sample size, then ORS is often overfitting. In this setting, we can use penalized regression methods, such as the lasso, the elastic net, the ridge, the adaptive lasso, and so on. And then we can define the penalized regression-adjusted AT estimator in the same way, just replacing the adjusted vector by the penalized regression. We can show that under appropriate conditions, this estimator is asymptotically normal, and the asymptotic variance is no greater than that of the difference in means estimator, which means the regression adjustment will improve does not hurt the precision of treatment effect estimation. Moreover, the asymptotic variance can be estimated based on residual sum of squares or Bootstrap. So we propose 3 types of Bootstrap procedures to estimate the variance. These procedures are widely used in linear regression models: the weighted bootstrap, the residual bootstrap, and the paired bootstrap. And we do the bootstrap for the treatment group and the control group separately and independently. And we show that all these bootstrap procedures are valid for influencing the average treatment effect in the following sense. They can conservatively estimate the limiting distribution of the penalized regression estimator, which performs at least as good as the method based on residual sum of squares. Let's return back to the PAC-man data. So in this data, there were 1,030 patients, and there were 59 covariates. And we also include their interactions in the regression. So the total number of covariates is more than 1,000. And we consider 4 methods to estimate the AG: the unadjusted difference in means, the ORS adjusted method, the lasso, and the lasso plus ORS, which use lasso to select variables and then use ORS to do a refitting. So this plot shows the results, and the AT estimator are the red circle. The bars are the 95% confidence interval, and the number on top of the bar is the confidence interval length. So we can see that all the confidence intervals contain 0, meaning that the effect of AT on patient survival is not significant. And however, it's interesting to note that the regression-adjusted estimator caused the AT estimate to decrease. This is mainly because the imbalance of the age and the estimated probability of death. And compared with the unadjusted estimator, the regression adjustment will shorten the interval length by about 20%. So these methods are more accurate. And compared with the OLS methods, we found that the lasso performs very similar adjustment. The difference is that the OLS will use 59 covariates to perform the adjustment, while the lasso only use 24 and 8 covariates to perform the adjustment. So it uses a much simpler and more interpretable model to perform the adjustment. And we also do a simulation based on the PAC-man data, and table 1 shows the results. We compare the different methods in terms of the Bayes, the standard deviation, the root mean square error, and we found that the Bayes is substantially smaller than the standard deviation. This is because all these methods are unbiased or asymptotically unbiased. And in terms of the standard deviation and the root mean square error, we found that the OLS adjustment decreases them by about 10%, and the lasso method further decreases by about 5%. Moreover, the lasso method uses much fewer covariates to perform the adjustment. We also take a look at the confidence interval. We compute the coverage probability and the interval length for 95% confidence interval. So the coverage probability is around 99%, which means that all these methods provide conservative confidence intervals. And in terms of the interval length, we found that the regression-adjusted method will shorten the interval length by about 10% when compared with the difference in mean. So as a summary, we proposed the penalized regression-adjusted AT estimator and established their asymptotic properties under the Neven-Rubin potential outcome model. Our analysis provides a principal way for investigators to analyze the results of randomized experiments when the number of covariates is large. And our analysis can be easily generalized to using more advanced machine learning methods to perform the adjustment. For example, we can use random forests or even deep neural network to perform the adjustment. And also, it can be generalized to more complicated randomized experiments, such as the stratified or block randomized experiment, and so on. Thank you.
So any questions here?
So I have one actually. So you partition the candidate in 2 groups, but you select like different sets of covariates for each group, right?
Yes.
But is it like reasonable to like share the same set of covariates? Because you're solving the same problem for the 2 groups, right?
Well, it's a very good question. So you can run one lasso for all the treatment and control group, not divided them. But in that way, under the randomization-based inference, the asymptotic variance can be larger. So we do the linear regression of model selection separately for treatment group and control group.
So I guess I didn't get the still motivation for the adjustment. Is it like purely for data fitting, or is it like for scientific understanding of like what's the key like covariance for maybe for the effect for the treatment? I don't know.
So do you assume that these two groups they may follow the different functional form of this? Because they have different penalized
Actually, we didn't assume any relationship between the covariates and the outcomes. So the randomness comes only from the treatment assignment. So the linear model here, the regression model can, we don't assume the correctness of the linear regression model.
So in other cases, if this two groups they truly follow the same functional form, so in that case, if we can also do this strategy, right? Fit different curve with two groups. In that case, as these two fitting function will they become identical in some sense?
I think if the linear model is actually true, then using the separate of treatment control group will hurt procedure, because for each group the sample size becomes half. So it would better to do the jointly. However, in the experiment, we don't know whether this linear model is true or not. And if you do them jointly, you have the risk of hurt procedure.
So any more questions? So if not, let's thank Professor Hanzhong Liu again. I think this morning session will end here, so we can enjoy lunch.